Let's look at solubility product constant KSP. So the solubility product constant KSP is the equilibrium constant for a solid. For a solid substance dissolving in an aqueous solution. Okay. Solid substance dissolving in an aqueous solution. It represents the level at which a solute dissolves in a solvent. It represents the level at which a solute dissolves in a solvent. So the more soluble a substance is, the higher the KSP. The more soluble a substance is, the higher the value of KSP. The higher the value of KSP. Okay, so let's consider a general reaction. Consider a general reaction. So consider a general reaction. A solid forms C aqueous plus D aqueous. Okay, so this is the general reaction. So we can to solve the KSP, it is necessary to take the concentration of the products. So the concentration of the products, which is C and D, and multiply them. So if there are coefficients in front, you can see there's a C, there's a D. If there are coefficients in front of any of the products, it is necessary to raise the product of that coefficient. Okay, so we need to raise them. So in this case, our KSP for this general reaction, so KSP will be equal to the concentration of C raised to the power C, concentration of D raised to the power D. Okay, so note that the reactant A is not included in the KSP equation. So solids are not included when calculating the equilibrium expression, because their concentrations do not change the expression. Any change in their concentrations are insignificant and therefore omitted. So hence KSP represents the maximum extent a solid can dissolve in a solid. Okay, so straight away let's look at an example. We see how we can write the KSP expression. Example. What is the solubility? What is the solubility product constant? What is the solubility product constant? Product constant expression for magnesium magnesium fluoride. Okay, so solution. So first of all, we need to dissolve the substance in water. We dissociate it. Okay, so we have magnesium fluoride, which is a solid, so magnesium fluoride then will form magnesium ion. You need to dissociate the salt. Okay, so magnesium, then this one will give us magnesium ion aqueous, then plus fluorine aqueous. So since there are two there, so this is the balanced equation. This is the balanced equation. Okay, so KSP will equal to concentration of magnesium ion times concentration of fluoride ion squared. Okay, so that is our solubility product expression. Okay, so we can have another example. What is the solubility constant? We just change the salt here. Same question. So what is the solubility constant product expression for silver dichromate? For this one, okay, silver dichromate. So let's dissociate the salt. So silver dichromate, solid. This one now will give us silver, since there are two here. Okay, so we have silver ion aqueous. Okay, then the dichromate plus dichromate aqueous. Okay, so it will look like this. Then now we write the KSP. We omit the solid, so KSP will equal to silver squared, okay, concentration of silver ion squared, then times concentration of the dichromate. Okay, so that is our KSP. All right, so now we can as well calculate the solubility. So let's have another example. So in this case, we've been given the KSP, then we need to calculate the solubility. So KSP for silver sulfide is 1.6 times 10 to the power negative 49. Calculate solubility. Calculate solubility in mole per liter. Calculate solubility in mole per liter. Okay, in mole per liter. Calculate solubility in mole per liter. Okay, so we do the same thing. First of all, we write the equation solution. So write the dissociation equation first. So we have silver sulfide solid, then forms silver to aqueous, then plus sulfide aqueous. Okay, so that is the equation. That is the equation. So from this we know our KSP would be silver ion squared, then times sulfide. Okay, so now KSP is given. We need to calculate the solubility in mole per liter. So let solubility be S. Let solubility be S. Let solubility be S. Okay, so we are now going to use our equation since our solubility is S. So from this equation, the concentration of silver is equal to 2S. You can see there clearly it shows 2S. Our solubility is S. Okay, then the concentration of sulfide is equal to S. From the equation, then now we use our KSP expression. So KSP is given, which is 1.6. So KSP 1.6 times 10 to the power negative 49, which is equal to now we substitute into the equation. Okay, so we have silver here. Concentration of silver is 2S, so it will be 2S squared. Okay, then this one, concentration of sulfide, which is S, so it comes to that. Okay, then now here this is it will give us 2 squared, that is 4. Okay, S squared times S, so it will give us 4S cubed, which is 1.1 is equal to 4S cubed. It is coming to that. Okay, then now we need to find the value of S. So here we know we can simply say S cubed is equal to 1.6 times 10 to the power negative 49 over 4. So you divide that number. When you divide by 4, then you are going to get 4 times 10 to the power negative 50. Okay, so that is our, when you divide, so S cubed is equal to that. Okay, then now what we need is to calculate the value for S. So let's calculate the value for S. So we know that since it is cubed, so it will mean S is equal to square root, then 4 times 10 to the power negative 50 cubed. Okay, you know how to do this simple mathematics. Okay, so S is equal to the cube root of that, which is giving us 3.42 times 10 to the power negative 17. So that is the cube root. Okay, so now we know the value of S. Remember now the concentration of silver is equal to 2S. Concentration of sulfide is equal to S. Then now we substitute. Okay, so in this case, for silver, concentration of silver is equal to 2 times that, which will give us 6.8 times 10 to the power negative 17 more per liter. So that is the concentration of silver. Then for S, it's the same. Okay, concentration for sulfide, which is equal to 3.42 times 10 to the power negative 17 more per liter. Okay, so that is how we can solve such type of a problem. Okay, we can have another example, but I'm sure this one is similar. Okay, for the sake of solving, we can just solve it. Okay, so let's solve the next example. Next example, the solubility of magnesium hydroxide. The solubility of magnesium hydroxide at 298 K is 1.71 times 10 to the power negative 4 more per liter. Calculate the solubility. Calculate the solubility product. Calculate the solubility product. Okay, so here we need first of all to write the equation. Magnesium hydroxide solid. Okay, then forms magnesium ion aqueous, then plus we have 2 hydroxide plus hydroxide ions. Okay, then now we know the solubility of magnesium hydroxide. We know the solubility of magnesium hydroxide. So this one, that is the solubility of magnesium hydroxide. You can see here, magnesium hydroxide to magnesium ion is a 1-to-1 ratio. So meaning that the concentration for this is just the same as that. Then this one is 1 to 2. Okay, so for magnesium ion is equal to the same 1.171 times 10 to the power negative 4 more per liter, since the mole ratio is 1-to-1. Then for hydroxide we are going to multiply. It's 1 to 2, so it will be 2 times 1.71 times 10 to the power negative 4 more per liter, which is giving us 3.42 times 10 to the power negative 4 more per liter. Okay, so this is for the hydroxide ion. Then now you write the KSP expression. So KSP will equal to magnesium ion times hydroxide ion squared. Then now you substitute the concentrations into the expression. So for magnesium we have 1.17 times 10 to the power negative 4 times 10 to the power negative 4 more per liter. Okay, then for hydroxide we have 3.42 times 10 to the power negative 4 more per liter. per liter squared. Okay, then we can here we are considering the units. Okay, so you square this number, you square it, then that's when you multiply. So when you deal with the numbers first, we are going to find 2.0 times 10 to the power negative 11. 2.0 times 10 to the power negative 11. So let's now multiply the units. Okay, let's see how the final units will look like. So here we have more per liter times this one is squared, more squared over liter squared, more squared over liter squared. Okay, so if we multiply more squared, more times more squared will give us more cubed. Okay, this one it will be since it is so this one, the first one. Okay, so we have more per liter, then more squared over liter, so we square this. Okay, so this one is the same as maybe for those who are not, let's follow it. So it is more, okay, then times more over liter. So now when we multiply, it is giving us more squared over liter squared, Okay, so now we multiply that. So liter times that, it will come to liter cubed. Okay, so this one now liter cubed, like that. So that will be the KSP. So more cubed per liter cubed. Okay, so that is how we can calculate the KSP. Okay, so now we can look at the important effects. How is this solubility affected? We have the common ion effect, salt effect, ion pairs. How do these affect solubility? Important effects. The first one, for highly soluble ionic, for highly soluble ionic compounds. For highly soluble ionic compounds, ionic activities must be found instead of the concentrations that are found in slightly soluble solution. Then for common ion effect, the solubility of the reaction is reduced. Solubility is reduced by the common ion. Solubility of the reaction is reduced. Solubility of the reaction is reduced by the common ion. Okay, so for a given equilibrium KSP, and for a given equilibrium, a reaction with a common ion presents a lower KSP. Okay, so the reaction in which there is a common ion, so the KSP will be lower than the reaction without the ion. Okay, so meaning that the reaction without a common ion, the Ksp will be higher. Okay, then we also have salt effect. Salt effect or diverse ion effect. Diverse ion effect. So having an opposing effect on the Ksp value to the common ion effect, and common ions increase, and common ions increase the Ksp value. Okay, so uncommon ions are ions other than those involved in equilibrium. Okay, we also have ion pairs with an ionic pair, a cation, and an anion. A cation and an anion. The Ksp value calculated is less than the experimental value due to the ions involved in pairing. Okay, so to reach the calculated Ksp value, more solute must be added. Okay, so in conclusion, we can define solubility. We can define solubility as the amount. Solubility as the amount of solute that can be dissolved. Amount of solute that can be dissolved in a given amount of solvent. Okay, that concludes our topic on the chemical equilibrium. Okay, wishing you all the best. Thank you.